back and we'll start to do the ones that we're not so good at, you know, the ones that we now are learning how. All right, here is
Are we turning back in after that?
all right, if you look on page 302, and we're just going to get a brief start here with kind of some fundamental notation things here, because this is kind of a breaking point. I mean, we're done with the first half. I mean, we're over halfway in days. We're really over halfway in amount of material, too, because we do have a fair amount of review time towards the end, which is kind of nice and a little easier on you, because a lot of it is in class time. I mean, we spend a lot of time, more time than we have been doing when we get towards the end, just in class stuff, and not a lot of homework at that point. But we have a ways to go until we get there. But it is, you know, the first half of the class, if you remember when we first started at the very beginning of the year, we said that calculus is really made up of two things. The first are two main ideas. The first one is slope of a curve. Okay? What is going on with slope of a curve? I mean, because we've learned about slope of a line in algebra, you know, average rate of change, slope between 2 points. But what does it mean to do slope of a curve? Or what does it mean to do instantaneous rate of change? You know, what can that be used for? And that actually started up in the study of when they were trying to, you know, Galileo and astronomy and looking at the stars and telescopes and optics and refraction and stuff like that. That's some of those questions were coming from that area. And this idea of the tangent line and all that. Well, as we found, as we investigated that, it turned into all kinds of applications. We got optimization from that. We talked about maxes and mins with related rates, like the shift problem we just did, and all kinds of different things, because things in real life are in motion and they're not in constant motion. And so this allows us to handle situations of all kinds of a variety of things. And so it's kind of a big deal. All right? And then the second thing the calculus studies is areas of weird, and I'm not sure they ever use that word, but I'll use it. The areas of weird shapes. And just like slope of a curve, you know, we know how to do areas of circles and rectangles, you know, a lot of things with edges and straight lines. But when you get into something like this, you know, how do you calculate the area? Because clearly that has an area. Clearly that encloses a fixed numeric area. But how in the world do we find it? Okay? Well, so there's kind of a connection between these two questions in the sense that they're both things we can do with basic types of shapes or basic lines. But if the problem gets more complex, how do we handle it? And what you're going to find is there's a lot of similarities. As a matter of fact, it seems like those are two really totally different types of problems that shouldn't have anything to do with one another. Well, the reason calculus is what it is because there was found to be this kind of connection between them. That there's a lot of similarities between how these are done. And then a lot of applications were offshoots of it. Okay? All right. So that's where we get this thing that they're talking about on page 402. It's called the definite integral. Okay, the definite integral. And it's, some of you have been asking me about it on your calculator. It's just kind of this S-shaped thing. And we'll put an A there and a B there. Now it's important where those are, actually. That the A's down on the bottom and the B's on the top. That matters. When we read that the integral from A to B. We read from down on the bottom one up to the top one. Okay? F of x dx. Now we're going to learn about why this is an S-shaped thing, and we're going to learn about what that dx is doing there. But for right now, the dx, well, you probably can guess what we're going to think of it. Same thing we do with derivative. What do we think of when we see dx? with respect to x in terms of x. This just means with respect to x. What we're really going to focus on is this part. So the dx, don't worry about it. It's there. Now, it might be dt or du or dr or dz or whatever. It doesn't matter. It just means with respect to. So it means our function here is in terms of x. That's all it means for right now. Okay, now later on, we'll see why it's there. Okay? So this is read the integral of f of x from a to b. The definite integral of f of x from a to b. Okay, just like when we started with derivatives, I just told you, hey, this little slash we're going to call f prime, and it means slope, right? And then we just went from there. Well, we're going to do the same thing with this. Now, what does this mean? Okay, so f prime means slope. We call this integral, but what's integral mean? It means the signed area between f of x and the x-axis from x equals a to x equals b. It means the signed area between f of x and the x-axis from x equals a to x equals b. Okay? So, picture of that, like what you see on in your book on page 304. If this was A, this was B, we're talking about that area. The area between the curve and the x-axis, in between. So A is like your left endpoint, B is like your right endpoint, which is what we're used to A and B. That's called the definite integral. Now the answer to that's just going to be a number. Just like f prime of 7 is a number. Just a number. It's the slope of the curve at 7. Okay? So, if we have this problem right here, sometimes we put parentheses around that 2t plus 1, but often we do not. So on some of your homework, you're going to have problems like this. Okay? Now what does that mean? Well, think about what we just said. It means the signed area between that function. What function? 2t plus 1. We don't, the dt we don't care about. It's just there. It means t's are variable. I mean, that's all it's doing. So it's really not doing anything else. We really just care about the 2t plus 1. So whatever that graph looks like, between it and the x-axis, from -1 to 2, there would be an area. Okay? So your next move would be to do what? You can plug in the endpoints, but I mean, before you do that, draw a graph. I mean, I think you need a picture. If you're going to do an area, you better know what the picture looks like, right? If you're going to do an area, you better know what the picture looks like. So we need to draw a picture. Okay? So what's the graph of 2t plus 1 look like? Or what do we say the graph is? Y equals 2t plus 1. That's what we're doing. So it's a line, so we're going to go up 1. And then we're going to go up 2, over 1, and up 2 and over 1, and down 2 and back 1, right? That kind of thing. Something like that. Oh, now that's interesting. So from -1, this is up here somewhere. Okay. Well, that's kind of a weird looking picture. Where would I shade this? Where's that area? Above and below. Wouldn't it be this too right here? Remember, it's the area between the curve and the x-axis. So, and it's from -1 to 2. I picked kind of a hard one right off the bat here, but that's okay. We'll study some other stuff, and then we'll come back and finish this one. But wouldn't it be that area there, because that's between the line and the x-axis, and then it would also be this area here, right? Which is essentially what, 2 triangles? Now, that's how we're going to start on some of our homework, is just basic geometry shapes, right? Because we know how to do it, okay? So the answer to this problem is just going to be the area of those 2 triangles added together, right? And so we're going to have to do some calculating here in a second. But before we do that, we should talk about what does it matter that that area is below the x-axis? I mean, well, I mean, I'm asking you this, and you don't really have anything to base it on. I understand. You know, it doesn't matter. I mean, should it matter? I don't know. It might. Maybe it does. Maybe it doesn't. Well, your background with area is always positive, right? I mean, who's ever heard of a negative area? But go back to our definition. The signed area. Well, what we meant by signed area, meaning can be positive, can be negative. And you might be doing this in physics. Have you done any area stuff in your velocity with distance? Did you talk about that? Because we've talked about that, velocity and distance. We're going to talk about that some more tomorrow. But it turns out it does matter. Okay, it does matter that it's below the x-axis. Okay, so here's I'm going to show you this thing next, and this maybe will help a little bit. Okay, so here's a picture, obviously a piecewise function. It's got like a part of a circle. It's got a bunch of other straight lines. The nice thing about a picture like this is we can just use geometry. The areas will all be geometric shapes that we can do area. So it's not going to be a weird kind of curved thing like a parabola would be, or a cubic, or a sine wave, or something like that, right? But it's going to be these basic kind of shapes. All right, so now, if I would do the area from C to D, okay, that's just going to be a rectangle plus a half circle, right? Now, look on page 303. Look down at the bottom of page 303 to kind of see what we're talking about here, okay? On page 303, the first one down there at the bottom, what shape is that? The blue shaded area. That's a trapezoid, right? And the area of a trapezoid, we'll get to in a minute, right? Hopefully remember the geometry. So we should be able to do that. Okay, the next one is just a rectangle. If you have a horizontal line, if you graph a constant, the integral of a constant would just be a rectangle, right? It would just be a rectangle. So that'd be easy. And then that other one, could you draw a line there and make that into a quarter circle and then a triangle, right? So you could do that area too. So a circle is pi r squared, and then take a quarter of that, and you could do that. So we could find this area right here, right? It's looked at 1, 2, 3, 4 by 2. So this rectangle right here would be 8, which is where this 8 comes from. And then this circle would be a radius 2. So pi r squared, 2 squared is 4 times pi is 4 pi, but then you do a half of that would be 2 pi. So we got 8 plus 2 pi, okay? And for all you long dividers out there, on a test it would not be important to take 2 times 3.14159, do not do that. Just write 2 pi. Okay, so that's simple enough. And what if we did the area from D to E, okay? Trapezoid, okay, so we could work on that, and that'd be 3. All right. But now the question becomes, what about this area here from A to B? What do you notice the answer is? Negative. Well, that kind of makes sense, I guess. If it's going to matter that the area below is different than the area above, then maybe it makes sense to be negative. And that's what it is. So the area from A to B below is negative. If it's above, it's positive. So this little triangle, this little piece of area we were talking about over here is going to be negative. And the area above is going to be positive. Okay. Now, what do you suppose the area from B to C is going to equal? -3, or no, -2.5. 0. Because you're taking a negative piece of area plus a positive piece of area, and they're going to cancel each other out, and that's going to be 0. Okay? Now, what if we do the whole thing? Well, that's going to be some negative area here, okay, which we said was -6. Then it's going to add on some more negative area, so the area is increasing. Decreasing. It's getting more negative. Now we're adding on some positive areas, so the area is actually going to start going up, getting less negative. Now the area is still increasing because we're adding on more positive area. And now we're adding on more positive area, so the area is continuing to increase. But it's increasing, but the blue graph, it was increasing at a decreasing rate, right? Because that line was going, oh, those terms are sounding a little familiar, right? Increasing, getting more negative, getting less negative, right? Some more of those connections a little bit we were talking about. We're going to be getting into those more on Friday and Monday and so forth, how that kind of fits in with stuff we've done. Okay, now, one last thing on this picture. I told you that it was important, the A and the B, where they were. And when we read this, it says the integral from A to B. Okay? So if I was to write this, if I was to write the integral from 1 to 5 of f of x dx, how does that compare to if I put those backwards? And we would want to think of that as backwards. We want this bottom number to be the little number and the top number to be the big number. That's the normal way to do it. That means you're going from left to right, from 1 to 5. This one is saying from 5 to 1. That'd be going backwards. Well, would it be negative? It makes sense. If you're going the opposite direction, it would make sense that maybe that makes everything opposite. And that's exactly right. So if we go, now we don't normally see it written that way. We don't normally want to write it that way. But sometimes in problems it just happens. Okay? Or you're given it that way in a problem. I wouldn't want you to ever write an area that way. But if the problem is given that way, you might have to. So, here they do the area from B to A. So look what you got. It sweeps it backwards from right to left, and look at the area. It's positive. And look at the integral. It goes backwards. It says -2 to -5, right to left. So what that means is if you go backwards with your integral, everything's opposite. Stuff below is positive. Stuff above is negative. Okay? All right. So now let's go back to this problem we were working on here. So let's do this little triangle. We're going to need to know where that crosses right there. How do we know where that crosses? Because of the slope, right? We went down 2 over 1. So you'd go down 1 over a half. So that's got to be a half, right? So this triangle would be half the base times the height. So it would be 1/2, the base is a half, and the height is 1. Now you could put a negative on that 1, or you could just do it and then say, hey, it's below the x-axis, I know it's got to be negative. So you'd get 1/4, and then you'd say, okay, but that's negative. Okay? So that's the area of that little triangle. The big triangle is what? Well, it's half the base. What's the base? 2.5 would be what? 5/2. And the height, how do we get that height? How'd you get 5? Yeah, but can't you plug it into the function too, right? You can just plug a 2 into the function too, right? So it's just the y value of the function. So that'd be 5. Okay, so what is that? 25 force. So, oh, whoops. Got to add, and then we got to add those together. Doesn't it make sense? The total area would be those two added together then. So that would be 6, right? But you wouldn't have to simplify it, right? 24 force, leave it, that's fine. But 6, probably good habit to simplify. So we get 6. That would be this area, so that would be the value of this integral. The value of a definite integral is a number. It's a fixed piece of area. 6 is that integral, that area. Okay? Little piece of negative area added to a bigger piece of positive area. All right, so you will have some problems in your homework that will be like the bottom of page 303. They'll give you an integral with a picture that you can just use geometry to calculate those areas. Then there's going to be some homework where they give you a function like this. Now they might use x's, they might use t's, they might use u's, they might use r's, it doesn't matter. You would graph that picture. They might give you a v graph. Oh, there's one that they might give you. that we should probably talk about real quick. What is that graph look like right there? No, I'm sorry. I thought when you said I thought you were saying something. Half of a circle. Now, why is it half of a circle? If you square both sides, you'd have this. If you add that over, you'd have x squared plus y squared equals 9. That's 0, 0, center, radius 3, right? Radius 3, 0, 0, center, radius 3. But why is it only half? Well, it wouldn't be a function, but what would make this a whole circle? Plus or minus. When you square root, you would get plus or minus. Plus is the top half of the circle, minus is the bottom half of the circle. So if you get an integral with this function, you know it's a half circle, so you can draw. Okay? So those are two of the things that will be in your homework. One where a picture's already given to you, you just do the geometric area. Somewhere it'll give you a formula, and you'll have to draw the picture yourself. And it should give you a geometric formula, some triangles, some circles, some rectangles, that kind of thing. Okay? All right. Last thing. There are a couple of rules. There are a couple of rules with area that are kind of like they are with derivatives that we can use. Okay, and I want to run over those real quick. So in your book, turn to page 306. Okay, in the middle of the page, they show you this picture right here. And they give you a rule that says the integral from a to c of function f plus the integral from c to f is equal to the integral from a to b of function f. Now let's think about that. It should make total sense. Right here, area. The area from a to c plus the area from c to b should equal the whole area a to b. Doesn't that make sense? So c's in between there. It just means if you add this piece of area plus this piece of area, you get the whole area. Okay, so it seems like just a very common sense, no-brainer kind of thing. But what if, and this is where you got to think about what we've just been talking about. What if you had a picture where the c was not, what if you had a picture where the c was not in between them? Would this equation here still work? Okay? What if you had a picture that went like this? Here was C, here was B, and here was A. Okay? Now, let's look at these areas. Here's a blue area. Here's a red area. And then we got the whole area is the green area. And notice I even put the A and B backwards. Okay? Let's think about this now. The area from A to C. Now, time out. Let me make one change. I don't like the A and B backwards. Let's make the A there and B there. Okay. So now, what about the area from A to C? The blue area would be negative, right? Because we're going backwards, right? A to C, that's backwards. So that blue area would be negative. I don't know what it is, -7, whatever. What about the area from C to B? And it's the whole thing. So think about what you would have if you took the blue negative, added to the whole green positive, what would you have? You would have the red, and it'd be positive, right? Because this blue negative would cancel out part of the green positive and leave you with just this, which is the area from A to B. So it still works. So even if C is not in between the A and the B, this little equation still works. That the area from A to C plus the area from C to B is still going to be the whole area from A to B, even if the C is not in between them, like it is here. Okay, now, what kind of problem will you have where that will be important? Well, let me just draw one up here. So I think that there's some like this on the homework. So let's say you had the area from 1 to 3 of F. They just told you that was 4. And then they told you the area from 1 to 9 was -3. And they wanted you to tell them what the area is from 3 to 9. Anybody got an idea what they think it would be? Yeah, I mean, something would be like the C, something would be like the A, something would be like the B. Anybody just have a guess without writing anything down? Well, okay. Here's how I would do this. First, I would look at which one's the whole area. The 1 to 9. So that's got to be the A and the B, right? So the area from 1 to 9 has got to equal the area from 1 to 3 plus the area from 3 to 9. Doesn't that make sense? The area from 1 to 3 plus the area from 3 to 9 has got to equal the area from 1 to 9. And now you just put it in like a little equation. What's the area from 1 to 9? -3. What's the area from 1 to 3? 4. What's the area from 3 to 9? Yeah, we don't know. X. So what's the answer? -7. So that's how you would answer a question like that, by knowing this rule, this sum rule, where you can add up pieces of area to get whole area. Okay? So that's something that may show up in the formula. That's a rule we can use with integrals. And then there's two others, and I'll show you a quick example and then leave you a little bit of work done. The first two rules in the box on page 306. One is the sum rule, which says if you add or subtract different functions together in an integral, you can split that apart into separate integrals. Okay? I'll show you where that comes into play here in a minute. And then this one says if you have a constant, now think about what we did with derivatives. If you have a constant in front of a function when you do a derivative, what do you do with it? Just leave it there, it just hangs out, right? Well, look what if you have a constant in front of a function here? You can just bring it out in front, just let it sit there while you do the area of the inside part. Okay? So let's do a problem where both of those two things come into play. And then I think after that you have everything you need for the homework problem. So let's say in this problem I'm going to give you this. So if you want to jot this down, you can. I'm going to give you that u squared du from 1 to 3. Okay? I'm just going to tell you that is 8. Okay? Now you wouldn't know what that is because think about it. I mean, if you were going to, what would a picture of that look like? That's a parabola. So if you were going to draw it, now don't draw this because you wouldn't in this problem. Here'd be your parabola from 1 to 3. Is there any geometric formula to find that area? No, because of the curve, right? All the ones we've done so far have been triangles and trapezoids and half circles, right? Geometry stuff. We don't know what that area is, so they just have to give it to us. So they're just going to tell us it's 8. Now later we'll know how to find that, but right now we don't know. So we'll just say it's 8. All right. So then they give me this problem. Find the integral from 1 to 3 of 4 minus 2t squared dt. So this is what I'm supposed to find. Okay? Well, if I was going to draw a picture of that, what would it be? Upside down parabola. So clearly I would not be able to find this area because if I drew an upside down parabola and shaded the area, it'd be curved and it wouldn't be a geometric shape. I couldn't find this area. Okay? But I can use the rules that we just talked about and this thing they just gave me to be able to do this. Here's what I would do. First of all, I would split this into two integrals. I would split this into 4, and you always stick a dt on, or dx, or whatever on every integral, since it's k, we use dt. So I'm going to split this into 2 integrals. See how I did that? Okay? Now, it's kind of like we did with derivatives. If I'm doing the derivative of x squared plus 3x, I do the derivative of x squared, and then I add it to the derivative of 3x. We just never wrote it out as, notation-wise, but here it kind of pays off to do that. So see what I did? I just split that into two. Anything that's add or subtract, I can do that. Now, what can I do with that 2 on this one? Okay? So I can take that 2, I can pull it out front and just let it sit there. Okay? Now, let's look at these two individuals. What is this integral? Isn't that this? So isn't this thing right here 8? So this is 2 times 8. So that's 16. Right? T squared dt is the same as u squared du is the same as x squared dx, right? They're all parabolas. Same thing. Just different variables. All right, now what about this? Couldn't I draw this one? Remember, the first thing we said is they might give you a function that you can just draw and it'll make a geometric shape. This is a function, right? This is right here, f of x. This is in the place of f of x. This is our y equals 4. What's the graph of y equals 4? Just a line up here at 4. From 1 to 3. What's that area? Isn't that also 8? Because it's 2 wide and it's 4 tall. So that makes a rectangle of area 8. So this integral right here is 8. So at this point, the only way we can do definite integral is the picture that we draw gives us a shape that's geometric that we know how to make that, calculate that area. Otherwise, we have to be given at this point. Okay, and what's 8 minus 16? Negative 8. So the answer to that problem will be negative 8. That's how you do it. Okay? So I think that's everything you need to be able to get going on the homework. So, everybody needs one of these sheets, chapter 5. Okay, take a guess at what numbers you're going to do. Not which ones you want to do, which ones you think I'm going to do. Okay, here's what we're going to do. The first line, stop at 36. That's his sign. Top line, stop at 36. Okay? But most of them are these, here's a picture. Oh, it's a rectangle, 4 by 2. 8. Good. Okay, next. Right? Most. Not all of them. But like one like this, you might have to do a little more. Okay? It's not a holiday. Tomorrow. Oh, it is actually. But not everybody celebrates actually. And not everybody celebrates Valentine's Day. So, you got to be politically correct. We don't celebrate Valentine's Day. Why are we getting through all? You guys haven't had a homework assignment in a day.
A day, yeah.
2 days. You were pretty good. If you were still doing the packets on Monday, anyway. That's true. You've been working on it. That's what I'm cutting.
Yeah.
Well, just be patient. That may happen. You never know in the near future. It happened yesterday. Surely could happen twice in a week. Okay. Let me slow down.